As you will see, the idea here is to integrate a nuclear reactor into a floating platform of the type that is used in an offshore or gas, oil or gas operations. And so we're taking advantage of that enormous experience and expertise that exists in that industry in our project. And that is currently taking place through the collaboration with this company that is based in Norway. That basically designs and builds a platform for the oil and gas industry. Yes.
Just a quick question: is that like Neil Tadreas?
Yeah, one of the other. So that's myself with the funny leather jacket, and then Mike Golay and Neil over there, and those are our students. Okay. Carl is a consultant for. Was on our advisory board, also a consultant. He also is from as a non-union person. We're working also with Larry Conway. He's a retired engineer at Westinghouse. As you will see, our point design uses the Westinghouse AP1000 design, and Larry was heavily involved in the development of their passive safety systems. So another selling point for this concept, and we're going to get into all of this in a few minutes, is a very, very high level of passive safety. So no need for AC power under all design basis events and beyond design basis events, including a very, very long, prolonged station blackout, similar to what happened, similar to Fukushima. Okay, so what is it? Well, in very, very sort of high-level terms, it is indeed a combination of two established and mature technologies. Offshore rigs, light water reactors, we call it the offshore nuclear plant. Sometimes we put an F there to indicate that it's offshore floating nuclear plant. Now, interesting but not well-known fact, there is actually more experience in operating nuclear plant or nuclear reactors at sea than there is on land. And of course, this has to do with the naval reactors, right? For mostly submarines, but also aircraft carriers. So if you look at the total number of nuclear reactors that have been commissioned so far, commercial power reactors on land is of the order of 500 total, including the ones that have operated, decommissioned, and so on, and about 800 naval reactors. So the idea of, again, having a nuclear reactor out at sea is not entirely new. By the way, throughout this talk or the slides, you will see questions in red here, and these are really for you to sort of stimulate your thinking about how do we bring this thing to market? Are we taking the right approach? You know, these are not going to be strictly engineering focused questions. They're going to be more on the big picture. So, you know, in your mind, try to answer. So let's start, for example, with the big picture here, right? So, is there value in combining mature technologies? You were talking about innovation. So what is new about an offshore rig, and what is new about a light water reactor? Well, not much, per se, right? If you combine them together, is that a good idea or not? But importantly, is there value in using two established technologies to create something new, or would you rather start with a sort of a blank piece of paper and say, I'm going to change the coolant, I'm going to change the fuel, I'm going to come up with a balance of plant that is different from a traditional steam cycle, and so on. Right? It's always a balance. It's a risk and opportunity. You guys have heard a lot already, and you'll be thinking about more and more. Okay, so what is the motivation? What are we trying to do? Essentially, we're trying to address some very, very typical challenges of nuclear power plants. And you have them in the slides and so on, but if I were to ask you, don't look at the slide, just think about it. What are let's say, the 4 most important challenges that nuclear energy faces these days, right? It's a classic. Everybody thinks about always the same 4. So let's see.
Waste.
Okay, so what are you going to do with waste? We don't address that problem. This is not a design or a concept that is going to allow you to do anything new with the used fuel. Okay, so that's one. Yeah.
Public perception.
Public perception of nuclear energy in general, and in particular, what do you think it's on the public's mind most of? Safety, right? Big time. This will address safety. Okay, that's a good one. Yeah.
Capital. Security.
Security, okay, I'm going to bundle that with safety, but they are distinct and there are a lot of subtleties there. Yeah, this addresses it. Actually, as you will see, we'll get into this in a few minutes, I guess. This concept eliminates certain security threats, but it also introduces new ones, okay? And so it's not a slam dunk. I would say safety-wise, it is kind of a slam dunk. Security-wise, is not. The other one that you're going to bring up is capital cost, okay? And so in fact, this is the first one that we have over here. I would say the fourth, which always comes up, and we also don't really address here. I don't know if when you say security, you probably meant security in terms of resilience against maybe terrorist attacks and so on. Maybe you meant it that way. There is another aspect of nuclear security, which is proliferation of nuclear weapons, and that too is not. This is not about that. Okay, I would say this really addresses the two big challenges: are capital cost, or cost in general, and then safety. Okay, so those are the two main areas. So. When it comes to capital cost, I could show you, maybe I have it, or maybe I don't have that slide later on. It turns out that most of the capital cost is not in the equipment itself. This is kind of interesting, because you think the capital cost of a nuclear power plant, to say, well, it has to do with, I don't know, how much concrete I have, how much steel I have, and so on. Well, it turns out that that's, of course, important, but it's only about a quarter of the total capital cost. Where do you think the most of the capital cost is embedded in? Yes, construction. It's the construction itself. That's about 50%. It's the installation of and construction of the plant, which always for terrestrial plants occurs mostly at the site. And so it's bringing all the materials to the site. It's bringing and accommodating all the construction workers at the site for 4 or 5 years. It's building facilities that are used in construction. Some of you have had the fortune of visiting one of the two big construction sites in the south here in the United States, either Vogel in Georgia or Summer in South Carolina. Anyone has toured those? Well, so you will see obviously a big construction site, thousands of workers and cranes and so on. But you will also see that there is a big building next to where the reactors are going to be. And that building, they call it the auxiliary module construction building or something like that. And it's a building that they built to basically put together different components into large modules, and then put those modules into the layout of the reactor. And that building cost a fortune. Okay. And so the idea here is, can we reduce the amount of work that has to be done at the site? Because work done at the site costs a lot of money. It's not efficient. Okay, it's not streamlined. Instead, if you were able to construct your reactor mostly in a factory or here in a shipyard, which already exists and already has, sort of optimized, very, very efficient construction methodologies, processes, machinery, and so on, you're going to save a ton of money. The interest that you pay on your investment, and that is directly proportional to two things. The first is the cost of the material and the construction. The other one is the construction duration, how long it takes to build. And so this is going to be addressed in this reactor by essentially building not just the reactor, not just the platform, but the whole thing at a shipyard, and then basically sending it out to the site. Yes.
Which of those has licensing type fees?
Licensing type fees, you mean? So the licensing of a reactor is usually decoupled from the construction of the reactor. I'm not sure.
I've heard it so that it's kind of like, it's not that the materials themselves are that expensive, it's compliance with regulation with those materials or something like that. Like, I don't know if it's in nuclear grade.
In that sense, I don't think there is going to be a big difference. So instead of having your NRC inspectors at the site, you're going to need to have them at the shipyard. The only thing I would say is the learning curve from construction of multiple units is going to be a lot quicker to walk down if you are at a shipyard, because essentially the workers that build the first plant are the same workers that will build the second, the third, the fourth, the fifth, and so on. Whereas, again, when it's built at a site, you bring in workers that are going to work on that project, and then they're going to go off and do something else. So in that sense, there is maybe a little bit of an advantage, but we don't expect it to be a massive thing. Now, the construction is the front end of the project. The back end of the project is decommissioning. And again, for a terrestrial plant, it's done at the site. And do you have an idea for what is sort of the order of magnitude duration of a decommissioning project? In the US, but I guess worldwide is more or less the same. Does it take 1 year? Does it take 5 years? Does it take 10 years? What do you think?
5, kind of.
Between 5 and 10 years. I think most projects so far have been of the order of 10 years until you really essentially return to greenfield. Yes?
Aren't they looking at longer ones? Because, I mean, everyone's just done the safe store approach where because there's 3 approaches you can do. And the safe store approach is you basically have as much time as you need. You reduce staff and kind of slowly do it, but especially these early decommissioning ones, they don't have the decommissioning funds at maturity to fully pay for them in a 5 or 10 year timeline.
Right. So it's a big commitment. It's a big commitment by the companies, and in the US, I would say there is the added challenge of dealing with the spent fuel. Because as you know, in the US, we do not have a national repository. We don't have a functioning national repository, and therefore, all our spent fuel is currently stored at the plants, either in spent fuel pools, wet storage, or in dry casks. Okay, so once these plants are going to be decommissioned, unless the federal government takes the fuel, which so far they haven't been able to do, the spent fuel, typically in dry casks, is going to stay at the site. And that means that you need to maintain an NRC license. That's still a nuclear site, although you have dismantled everything, that you have sort of these totem look-alike casks sitting outside in a parking lot, and that requires an NRC license, it requires security, it requires a certain minimum, but not negligible operations to continue indefinitely. Okay? So here, just let me say, so here the advantage is that once the plant has ceased to operate, generate electricity, you would take it back to a centralized shipyard where it's decommissioned. And this is the same model that is currently used by the US Navy for decommissioning of their nuclear power submarines and aircraft carriers. So they bring it back to a shipyard, they take it apart, and that's done very efficiently and cost effectively. There was a comment or a question?
Yeah, and obviously the decommissioning is affected by discounting, so that's one thing. And you said there's only 2 factors: the time and the magnitude of the capital costs. My question is, how much effect does the variation in the financing option come into? I mean, is that a pretty standard thing, the financing? Or?
No, it's not standard, and I think if you haven't already covered that, probably you will in the course of this program. There are so many different models, right, for financing. You can raise capital on sort of on Wall Street, for example, but you could also engage the company that builds the plant to finance part of the project, or hold the project. I mean, the extreme in that sense is the Russian model, right? The Russians are now offering essentially full financing, including ownership and even operations of the plants that are building outside Russia. So that's like a radical approach. You just basically get the electricity, but they do everything else, right? So it's there are many different models, and the first part of your question was how sensitive is it to the financing? The interest accumulated during construction is hugely sensitive on financing because it's an exponential, right? If you look at the time value of money, it's an exponential. And so the difference between a discount rate of 5% and 10% is not just it doubles, it like triples. And of course, it depends on how long it takes to build it, but if the longer it goes, and the higher is the escalation. So there are huge incentives in keeping the discount rate low, which is something that we have very little control on. Wall Street decide if you decide to go Wall Street. But the other thing that we have control on is how long it's going to take to build it. And so if it takes 5 years or 3 years versus 7 or 8 years, it makes a huge difference. It's billions of dollars. Yes?
Speaking of Russia, what's your take on the floating nuclear power plant they're developing as a market?
Yeah. So there is Russia and now also China, right? They have announced and they have strong activities in developing floating nuclear plants. You will see in a moment the design that we're developing is very, very different. In their case, they're using reactors that are derivatives of icebreaker reactors, and basically they're putting them on barges. So they're not integrating the reactors into an offshore rig, similar to what we do. It's barges, and they're typically docked at the coast, whereas ours is offshore. And you say, okay, well, those are differences. Why do they matter? You'll see. So I'll point out why it is good to have it offshore versus on the coast, and also why it makes sense to integrate it in a platform versus a barge. There are some advantages in terms of stability, security, safety, and so on. So we feel obviously that the design we're doing is different and better. But the Russians, on the other end, are definitely more advanced in where they are in their design and commercialization. They're actually building one such unit in St. Petersburg, and the Chinese probably will just run through even quicker, because that's the way they do things these days in China.
I thought they'd already, the Russians would already, am I wrong about that? I thought they'd already done that to power some of their operations for the season. Is that not correct?
You thought the Russians had already commissioned floating power reactors?
For some submarine maintenance?
But then it's submarines.
Okay.
I mean, if you're talking about, so the naval reactors, there are plenty of reactors out there, but for power, for civilian power, as far as I know, there is no operating offshore floating reactor yet. Now, the other motivation is to expand the number of sites for nuclear power, NPP stands for nuclear power plants, okay? And so it turns out that's obviously the world map, and where you see red, the intensity of redness there means the population density. And so about 50% these days, 50% of the world population live within 100 kilometers of a coast, of either ocean or sea and so on. So that's where your customers are, right? So you want to be close to your customers, but maybe you don't want to be on the coast, as we've been doing nuclear for the past 40 years, because coastal land is becoming very packed, very crowded. It's also very valuable, right? People love it. Who am I talking to? Here is California, right? People love to live there on the beach and so on, and they don't want a nuclear power plant right next door. But on the other end, they want the electricity. So here the idea is, can we put these power generators close to your customers, but not right there where the customers are, right? So not interfere, a little bit out of sight, out of mind. So the site for the plant is offshore, but it's within territorial waters, and that's defined as 12 miles off the coast, okay? And we want that because the host country, if it's within territorial waters of the host country has responsibility for regulation, security, so it's not sort of no man's land, right? They have ownership of the plant. Another reason why we like this concept is you have heard, this I'm sure has been mentioned, or you just saw in the news, of the decisions by some utilities in the US to shut down some of the current light water reactors, our nuclear power plants. And it's mostly driven by economics, by the way. I mean, I hope you appreciate this is not due to the fact that the plants aren't safe or they're old. They are old, but so many components have been replaced that they're probably as good as new. So these are economic decisions so far, and the economic decisions are due to the fact that, particularly in deregulated markets, such as the Northeast or the Midwest, these plants are not making money. Why aren't they making money? Have you guys covered this? Has there been any...
Natural gas.
Natural gas prices very, very low, right, in the US now. We sort of won the lottery a few years back with shale gas, so we got plenty of hydrocarbons, they're cheap. So natural gas price, very, very low. That means nuclear is not competitive with natural gas. And then in many markets, I would characterize it as the unfair competition from renewables, which are very heavily subsidized, and also they're non-dispatchable, and the grid just takes that electricity when it's generated, and that of course reduces the prices, which in turn reduces the profits of baseload generators such as nuclear power plants. Okay, so why does the offshore floating nuclear plant address this issue? Well, because this is now a mobile energy source, a power generator, right? So if the local conditions of your market change and your plant is no longer profitable, move it. You cannot do it with terrestrial plant, but with this one you can. This is a mobile plant. That is not to say that you can move it, on a weekly basis, monthly basis, probably not even on an annual basis. But maybe throughout the lifetime of a plant, if you're thinking 60 years, which is typical, maybe you're going to move it a couple of times. Follow the money, right? Follow where the profits are. So that's an additional flexibility which doesn't commit the customer to a 60-year project. Maybe you can plan ahead for 20 years. The last, as we said, is safety, of course. And what is the big deal with safety in nuclear? Well, we can stay here, talk about this for 3 days straight. But the big deal is with severe accidents, right? I mean, all the design basis events at current plants are well taken care of with huge margins and so on. But every once in a while, a very, very bad accident happens, right? And so the Holy Trinity is from TMI, 3 Mile Island, Chernobyl, and Fukushima, of course. And why are these accidents very bad? Well, they're bad in many ways. First of all, the utility, the company that owns the plant, typically loses an enormous amount of money. He loses the plant and he loses a lot of money in the recovery effort. But I would say that most importantly, it really, pardon my French, pisses people off, because typically there are releases of radioactivity in the environment, and then some land gets contaminated and people have to be displaced. And I think that's really what makes people dislike nuclear. It's the consequences of these severe accidents. So with this design, with this offshore floating nuclear plant, we think the consequences, first of all, you can drastically reduce the probability of a severe accident to occur. And should a severe accident occur, you can very, very much reduce the consequences for people on land. And I'll show you how this is done in greater details. Yes?
I just have a question. In these plants, would the source of coolant be ocean water or something else?
Yeah, the cooling of the, so under normal operations, the cooling water goes to the condenser, and it's the ocean, of course. Under emergency conditions, the ocean is still the heat sink. Of course, we don't use seawater in the reactor. You never want to have salt water, coming into the core, the reactor, and so on. So, but through heat exchangers, you're going to remove, you're going to discharge, if you wish, the decay heat that is generated within the reactor to the ocean. So, short answer, yes, we use the ocean as the heat sink for both normal operations as well as emergency cooling. And you'll see the drawings and schematics and all of that. So, that's the motivation. Are we missing any important challenges? Well, we've already gone through this. The two that I didn't mention here were waste and proliferation. We just don't, that's not what this concept addresses. Okay, so we're not pushing the envelope in that sense. Yes?
What about increased operational costs from permanently on-site staffing that might actually
Yeah, that's a very good point. So while this addresses capital cost, and it's going to be greatly reduced, we think, we believe, your point is well taken, that the operating costs are going to be a little bit higher, because essentially the operators and the security guards will have to leave on the platform, because you can't move them in and out, and so you will have to pay them a little bit more. So that's factored into the cost equation. But remember that for nuclear plants, if you look at capital versus operation, capital is 80%, operation is 20%. So I am happy I can live with a slight increase or a small increase in operation cost if my capital goes down by, say, a factor of 2. Yes?
I know terrestrial plants construction is limited by environmental impact statements. As we're moving towards this offshore system, is there any sort of framework that evaluates where this offshore rig can be placed, and at the point in time where, technically speaking, it's mobile, will it be able to, if that makes sense?
Yeah, no, it's a very good question. So the answer is no, there is no existing framework for an offshore floating nuclear power plant, and that's one of the open challenges for this. It will have to be developed. What you have is regulations for nuclear reactors, of course, and also for the nuclear reactors that we want to use. For example, in 81,000, it's licensed, it's under construction, so that exists. And you have regulations for offshore oil and gas platforms. But now someone has to essentially marry those two sets of regulations, and probably you will need additional things that come out from the integration of the two technologies. So it doesn't exist. That's a very, very important challenge which has to be taken on. And the answer to the second question is that, of course, you can't just move it to a site and say, voila, now plug it in. So it has to be moved to a site that has been approved and therefore subject to whatever regulations are in place at that particular host country or site. There was another one. Yeah.
Let's see. In the challenges, so historically, a lot of the accidents have been related to the ability to maintain heating or cooling components. Right?
Yeah.
It makes me really nervous that you're thinking of going into the water because I'm not a nuclear engineer. What is the possibility of materials leaking into water systems, and how are you addressing?
Yeah, I'll get to it. Very, very low because of the nature of the safety systems that we use. They're fully passive, so everything is taken care of without having to rely on pumps or AC power. So the whole thing is very gentle and quite reliable. But so we'll get into that in a few minutes. Yes, and 1 and 2.
Stop delegating to me. Ask your question.
Either one.
Sorry, always
There's two things. I don't know how difficult it is and how expensive it is to get the, I know it's only 12 miles, but to get the electricity back on and switch on transformers, that's a safety thing as well. And the second question, I read some, this is not mine, I read this in some of the pre-literature. You've got an added security aspect by the fact that you've got 3-dimensional security to look at.
Right. You guys have all good questions hanging there because we get to all of this. So I have slides on security, transmission of power, all of that. Yeah, so we'll get to that.
So I just wanted to, Cindy, you asked a question about the radioactive material going into water. So, like I said, you walk on, so I'm not going to try and steal your thunder,
Yeah.
but Fukushima, for example, talk about this detritiation of Fukushima. The tritium level in the water at Fukushima from the accident is so low that you can actually drink it legally in almost, I think it's every single country in the world. So that's an example. Now, the government have to be seen to detritiate that water, which is costing them, I think it's almost $1 billion to do that, but they have to do it because it's like, otherwise you don't care about what you've done. So I'm just saying here, the reason it's so sparse is because the ocean is huge.
Right.
So even if there's a small leak from this, I'm not saying it's acceptable. What I'm saying is it would disperse so far into the water, actually the radioactivity level would be so low.
But now your impact is greater, whereas if it was on site, your impact would be, let's say, I don't know, 10 square miles, right?
Okay.
Now you're in the waterways and the potential of crossing into international borders.
Yeah, but I agree.
So let me jump in, not because I want to stifle the discussion, but I think you're both making good points. I think when you're dealing with the public and it comes to releases into the environment, it is really not acceptable to say dilution is the solution. You can't. Right? You can't. And so what we have to show is that either the releases are minuscule, okay, or if they are significant, which I don't think is acceptable either, then essentially there are really no consequences to population. But just say, hey, the ocean is large. That's not the right way to deal with it. I think we need to reassure that there is a very robust mitigation of severe accidents, and that's what I'm going to try to tell you in a few minutes. There was another question back there.
Oh, I just had a comment, to say, you just said that they have to, they're paying $1 billion to detritiate out. Then one of these goes down, then every nation on the coast in the world has to pay $1 billion to clean the water. So.
Yeah, well.
But that's just, I think that's what she was trying to make.
Yeah.
No, I can see the point. What I was trying to say was in an accident scenario, I think it comes all the way back around to what I really tout the whole time is education about it. It's just people are scared of it because they can't see it, they don't know about it. And yeah, that's what I was
I would say generally the nuclear industry has been woefully bad at communicating with the public. They are either the approach has always been fly under the radar. You don't want to be in the news. No news is good news if you wish. Instead of actively trying to engage, and that has to change. But it's not something that we want to take on as developers of this of this concept. I think it's a bigger question. Maybe a quick comment. Let me keep going because we're getting to a lot of these issues when you see what the design looks like, how we deal with safety and so on. So maybe we can expand that. But yeah, go ahead.
But there's a nuance in what we're just saying because that specific issue, I just want to get this in there, the Japanese issue, that tanker of water that was safe to do something with, the public perception of that risk led to a bad scientific choice. Because if there was another tsunami after that, and that would have been released around on the shore, it would have been a much worse incident than releasing it into the sea. And that was a public pressure that made a bad scientific choice.
Yeah, good point. So these next two slides, let me go quick because we already talked about the the decommissioning and so on. I'm going to make this point kind of early, and then we'll get back to it. It is a floating plant, so earthquakes, which of course were a big deal, they're always a big deal for nuclear plants in general because they are important initiating events. They can cause failures of components and structures and so on. They're eliminated by design because the thing floats, and so even if the ocean floor shakes, it's not transmitted. The other thing that may be less obvious is that if you put this reactor in relatively deep water, this is not that deep, but it's not. You don't touch the bottom, right? If you go swim, it's about 100 meters. Actually, tsunami waves are pretty small waves. Okay, so tsunami waves become destructive when they approach the shore because essentially the energy concentrates, if you wish, and so you have large amplitude of the waves. But when you're out there, a tsunami is not actually a big wave. Storms, different story, and I'll show you how the concept deals with that. Yes.
Just a question about how this plant is connected to the grid and whether this kind of questioning whether tsunamis are considered when it's already connected to the grid. There's already kind of thoughts about emergency protocol for disconnecting and kind of removing any kind of attachment to sea. I guess to land.
Yeah. So how is it connected to the grid? There is an underwater transmission line. This is now used quite a bit for all offshore, for example, wind farms. Right? They have a water that basically runs at the bottom of the ocean and then it surfaces at the coast. And so what you have on land is a switcher, and if there is any need to sort of disconnect the plant from the grid, you would do it there. That's an electric disconnect. You wouldn't physically remove the cable. There is no need to do so. We're basically designing the mooring system and the platform and the cable to be able to accommodate some motion of the platform without having to pull away the cable. Okay, can we talk about this? Okay, so what about the design? All right, so first some design guiding principles, and just read that one there. Does that make sense? The whole point here is this should be of interest to you. We're trying to accelerate the sort of the commercialization of this concept. Okay, so if you're a nuclear engineer, you know, or you may, if you're not, you may guess that if you're starting using new materials, new fuels, or components that are entirely new design, oh boy, you're in for a nice bumpy ride, right? Because you have to basically relicense and requalify all those materials. Who has a sense for how long it takes? For example, say that you're changing fuel, right? You're not using UO2, but you want to use uranium nitride or uranium carbide, some new fuel form. Do you have a sense for how long is it going to take to qualify that fuel before the NRC is going to tell you, sure, go ahead and now use it in a commercial reactor? Maybe not quite, but it's let's say between 10 and 20 years. So it's absolutely massive upfront program that has to take place before you can use it in a commercial plant. So don't even if you want to do something within the next 20 years, don't touch the fuel, don't touch the materials that go in the core. Don't perturb too much the design of heat exchangers, steam generators, and things like that. So that's the first principle there. Yes.
So on that topic is, would you say that the research for new materials, new ideas, new designs should be done by the universities or research departments in the companies, and otherwise we should just press on and then innovate whilst we're doing that, so it can be applied later?
It depends on what you mean by we. Who is we? Is this group or us? I put myself in your group as in like academics and so on. The answer is yes. We should. We obviously are not building these plants right ourselves, and so It's our job to think next generation, innovation, and all of that. If you are a nuclear company, I think you need to have a little bit of that as well. But if you want to bring something to market within the next 20 years, you have to use proven technology. You can engineer it in new ways, and it's exactly what we're doing here, right? I'm not changing the materials, but what I'm going to show you in the next slide, it doesn't look like a traditional nuclear power plant, right? And so it's, I think there is definitely a distinction of our roles there.
So is there a feeling that we definitely actually want to do stuff like this? You know, this sort of design?
You definitely
want to do this sort of design now, or is that people sort of waiting and going, we think there are better materials, we're going to wait 20 years for those materials to be licensed and verified and qualified?
I think what you're asking is how do you factor in these long delay in materials that you may need for your design? And the answer is, in some cases, let me take, I don't know if maybe that is an aspect, but let me take the TerraPower example, right? You heard about TerraPower, you know what they're doing. It's not a light water reactor, it's a sodium fast cool reactor. Now, sodium fast cool reactor is fairly developed. In fact, there have been a few demonstrations. There are a couple of plants that are even in operation, one in Russia, one in India recently, maybe one in China already. So it's a relatively mature technology. Now, TerraPower, it's a sodium fast cool reactor, but their core looks different. They have a refueling scheme by which essentially you can just feed it with depleted or natural uranium, and the reactor runs ultimately, because it's a breed and burn concept, so it runs on depleted uranium, and then what you get out is essentially waste that you can put. So in order for that scheme to work, you need to demonstrate that your fuel and the planet that protects the fuel can withstand up to, I think, 300 or 400 DPAs. You know what that is? Displacement per atom. It's a measure of the damage that a material receives or undergoes when it's exposed to neutron bombardment. Okay. Now that figure is ridiculously high, right? I mean, typically in our light water reactors, the peak plating DPA is maybe 15, maybe 20. So this is an order of magnitude more. All right. Now, you don't have currently a qualified material. So does that mean that, and in order to qualify, it's probably going to take between 10 and 20 years. Does that mean that TerraPower cannot build anything within the next 10 or 15 years? Well, their approach is, we're going to build the damn reactor as soon as we can. And the core at the beginning is not going to have all the beautiful features that ultimately we want. So you're not going to be able, on the first core, when you demonstrate the technology, to feed it with depleted uranium. And so what that means is that you can use qualified materials now for your cladding. And then as as the first reactor operates and you're gaining experience and all of that, in parallel with that, you're going to have a fuel qualification program that will take you where you want for the ultimate product. So that's one approach, right? That's one approach. But if you put a new material or a new fuel on the critical path to commercialization, then you're in for a 15, 20 years development, which is long. Does that make sense?
Yeah.
Okay, so the second guiding principle is we design this thing for construction. What that means is you can come up with beautiful designs, but if you can't build them effectively in a shipyard, then they don't work. And so what we have in mind here from the beginning is how are we going to build this plant in a shipyard? Okay, and so you'll see how that works. Essentially, it's a very vertical layout that you can start putting things on top of each other in parallel. So you don't have to sort of wait for one level to be done before you put in the next level and so on. So it will be Lego style. And lastly, for non-safety design features, we try to make them sort of multifunctional so that essentially every component in the plant has more than one function. That's very good for economics, but of course you cannot do this for safety systems because you need to have the redundancy. So, but you see. All right, so finally, after this very long introduction, what do these things look like? All right, so they are so-called cylindrical double hull floating platforms. We have two flavors of it. The OFMP 300, which means generates 300 megawatt, and the OFMP 1100 generates 1100 megawatt. So what you can see is, again, it's a cylindrical hull, so it looks like like a big cork, if you wish. This is the water line here, the water line there. So most of the plant is actually underwater. It'll be like an iceberg. Okay, and then you have the mooring system, which is not shown here, that essentially connects the bottom of the plant and the top there all the way down to the ocean floor. You can see the some numbers here that give you an idea of how big this object is. So for the small plant, you're looking at about 75 meter total, of which about 50 meters is underwater. Graph means depth underwater of the, right? And then the diameter of 45, and here a little bit bigger because this is the bigger plant. Now, a lot of thought went into that, sort of that design, and we used a lot of consulting from, a lot of advice from industry on this. But an important constraint or important sort of design objective was this thing is like, again, think it as a cork, is a floater, okay? And so it has a natural frequency for heave or pitch and so on, okay? And what do we know about things that oscillate? In general, this is like a physics one, right? It's vibrations, okay? So what would be a design criteria for you? If you have something that can resonate, right? The concern with things that oscillate is that you can have some kind of an external load that will make you resonate. If it resonates, then your oscillations are going to become enormous and bad things happen. Okay, so in this case, the external load are waves or wind or currents. Okay, and so for this thing not to resonate with those loads, you need to have a frequency that is similar or not the net. So the frequency, your natural frequency, has to be very different from all the frequencies of the external loads. Okay. Now here there is a little bit of a conundrum. You have two types of waves. One is tsunami waves, which are very, very low frequency and very sort of long wavelengths. And so that's at one end of the spectrum. And then you have storm waves, which are actually very high frequency and short wavelengths. And so you have a peak here, you have a peak there. And so we designed to have our natural frequency in between, because otherwise you have big resonance either with tsunamis, which are very rare, of course, or with storms, which are going to be a lot more frequent. Okay, and just throwing in a little bit of engineering so that it's not all about business and economics and so on. Now, one question that you could ask yourself is, why did you go with that design, like the cylindrical floater? If you talk to folks that do offshore engineering of these platforms, there are so many other types of platforms that we could have gone with. And you may be familiar with some of them, although these are schematics. Let's see, semi-submersible, right? If you think about an oil gas rig offshore, you probably don't have in mind something that is cylindrical. You have in mind something that looks like it's on stilts, right? And that's a semi-submersible here, or maybe even a jack-up rig, and so on. So, and there are other designs. There is essentially a sheet mountain, which is the like the Russian or Chinese. It's a barge. So why do we go with that other one? If you just think about it in engineering terms, let's pick whichever. Let's pick a jack-up rig. What are the drawbacks and what are the advantages of a jack-up rig? What do you think? Yes.
Drawback is that you can't move it.
You can move it. Actually, you can move jack-up rigs.
Oh.
Yeah. But it's funny. I mean, because these things are planted inside the soil, but you can't remove it. You could move it. Anything else about the jack-up rig that you don't like, or maybe something that you like? What do you think?
You break one of the legs. From an external incident, if you break one of the legs, you're not used to it.
Yeah, I guess it could buckle. What about earthquakes, right? So now it's attached to the bottom. If you have a shake, it's going to give you, everything on top is going to shake as well. So that's one thing. Let's find something positive about the jack-up rig.
Doesn't talk about it moving at all.
It's
waves.
Right. In terms of it's not gonna move up and down or anything. I mean, it's really fixed. Okay. And so that's a good thing. So it doesn't require mooring. It doesn't require mooring. And what about the ship mountain? The barge. Good and bad.
It's close to shore, makes it easier to service and bring stuff to.
So that's a good thing. Yeah. Right. Okay. It seems like a very simple design. I mean, we've been building ships for millennia, so that's easy. Anything bad?
It's close to the shore. That's a bad thing.
Okay, that's a bad
the tsunami waves will be big, and also you've got the cables just kind of tucked into the ship.
Yeah, all of that. That's true. I mean, in principle, you could have a barge that is sitting also offshore, right? I mean, you can have mooring and so on.
could facilitate a new breed of nuclear pirates.
That take off.
Take it.
Yeah. No, so it's a much less stable design than the cylindrical floater. Again, think iceberg versus think about the fight between an iceberg and Titanic, right? So which wins? Well, the iceberg, which is our design, essentially most of the mass is underwater. It's very, very stable. You can't move it, right? Whereas this one, when the ships, when they have big storms, it's gonna go all over the place, right? So it's a lot less stable for storms. The other thing is that it's more difficult for a ship-mounted reactor to be underwater, to be below the water line, and therefore have access to the ocean as a heat sink. Yes.
And there's limited capacity just due, like if you want to put a 1,000 megawatt electric reactor on a ship mounts barges easily. There's a reason the oil industry doesn't use ships as rigs; they use rigs as rigs.
Right. Yeah, that's a very good point. I mean, you'll see. Actually, you already seen it. But you've seen it here. But you'll see it again better later on. I mean, the reactor, inside this thing, there is an AP1000. I mean, putting an AP1000 in a ship is just physically, it would be an enormous ship. Okay, so this is it's more integrated, it's a more compact design. So that's okay, very good. So here comes the Titanic thing. So everything that floats has the potential of sinking. So history has shown us that there is no such thing as unsinkable ships. And so there is no such thing as an unsinkable rig either. So we put a lot of work into minimizing the chances that any of that these platforms would not be able to sink. So basically, all these levels here below the water line are all watertight. And also, this is a cross-sectional view of the plant. Essentially, we have 6 sectors. So not only axially, but also azimuthally. The thing has bulkheads that go above the water line, and they prevent, they really prevent sinking, because this is done also for naval ships. Essentially, they can take flooding of many different compartments without going down, and this is the same. It's the same approach. All right, so this is the OFMP 300, so it's a smaller thing. The reactor is at the bottom, essentially, because you want the center of gravity to be low. Again, that's for stability. Also, it's below the water line, so you have access to the ocean. The turbine is up there, so there are the steam lines that are not shown here basically go from the steam generators inside the reactor, and they go all the way up there, and that's where you have your steam plant. Okay, and then other necessary features of nuclear reactors are there. You got control room, of course. You have a spent fuel pool. So the way you would refuel this thing would be the same way you do it for terrestrial plants. You have a refueling floor, and you have a machine that you open, of course, the vessel. You have a machine that goes in, picks the spent fuel assemblies, pull it out, and then puts in the fresh fuel assemblies. And those spent fuel assemblies go into the spent fuel pool. And we've designed it to have capacity for essentially the lifetime of the plant. So here again, the engineering sort of option could have been: do we ship the spent fuel to land, to shore, or do we keep it there? And we decided that handling the spent fuel at sea would be bad, and so we're just going to keep it there basically. And then once the whole thing goes back to the shipyard for decommissioning, you would take care of that. Minor maintenance is done at sea. If there is major maintenance like replacement, I don't know, steam generator or some other major components, obviously you would do that in a shipyard, so you would have to take that thing back. This came up earlier. It's a different operations model. You're out at sea, you can't bring people in and out. They can't drive their car out to the plant the way they do at terrestrial plants. So basically this is designed with living quarters, which you can see there, and people would be out there for 2 or 3 weeks, and then go back and do 2 or 3 weeks of essentially off. Okay, so it's the same model that is used for offshore oil and gas. Yes.
Could you consider moving the control room away from the actual reactor facility?
Do it like remote operation?
Yes.
So we did, and in fact there was a concept that was developed or proposed by the French. You may remember it was called FlexBlue. Have you heard of this? These were undersea reactors, so they were actually sitting at the bottom of the ocean, and they would be remotely controlled. There are some security, safety issues related to the. I don't think we're ready for a remotely controlled plant. I think you want to have people that have control of the plant right there. So we consider, but we didn't want to have to answer that additional question. There are so many already challenges related to this, so we decided to go with people on board. That's one or two. Yeah.
I thought she was going to ask this. Is there any reason the control room is underwater?
No, not really, but it's we wanted it to be deep inside the platform, and that's for protection from plane crashes or ship collisions or things of that type. And it's, by the way, it's a hardened room, so most of the plates that you see here, the hulls and so on, are 5 centimeter steel. And this one is reinforced, and it's like a 15 centimeter, so it's really like a steel box that it's very, very difficult to get in. So it's mostly security / safety thing. This is what the OFMP 1100 looks like. So it's a much bigger platform, and you see this is basically the AP 1000 container. For some of you may look familiar. And the steam plant is up here, so you got the turbines, moisture separator, heaters, condensers, all of this. This is a very big platform, and there is plenty of room for all the good all the good components of reactors. Was there another question? Okay. So storms, right? So that's very important. It's out there at sea, and hey, if there is a hurricane, I mean, maybe you're not going to put one of this in the Gulf next year. Why ask for trouble? But you need to show that the plant can withstand very large waves and bad weather without moving too much. What are the issues, by the way, with oscillating or bobbing excessively? Some of this is obvious, but let's think maybe beyond the obvious. First of all, you're going to get seasick, okay? But that's maybe not a big deal. Okay. What else?
I was going to say reactor operators seasickness, like genuinely could be a problem.
Yeah. That's certainly an issue. Anything else? Maybe more severe? Yeah.
It's the same issues that they dealt with in the submarine program. So actual movement in the reactor area could cause problems for operations.
Right. But first of all, if you move excessively, all the structures have to be designed to be able to take that motion, which means maybe thicker, more expensive, and all of that. But also, it could become a safety issue. Why? This is an AP 1000. It's a passive plant. So if the whole thing starts to do like this, what could be the problem? Does anyone guess? Let's see if somebody else wants to answer before you go.
Natural circulation issues?
Natural circulation. So AP 1000 relies on natural circulation for decay heat removal, right? Natural circulation is based on what?
The Bushnell approximation.
Right. Yes, but so it's based on the fact that you have a heat sink at a lower elevation than, a heat source at a lower elevation than your heat sink, right? And so then warmer fluids want to go up and cooler fluids want. Well, if that's normal operation, that's great. If the whole thing moves and the heat sink and the heat source come to a closer elevation, then it's not going to work. Okay, so you need to prevent massive oscillations and so on. All right. So on this question, we work with our friends at Savant Marine, and what you see here is two tables. This is the forcing function, which means this is the height of the waves, the period of the waves, the velocity of the current, the velocity of the wind. And here you have 4 columns. One for the 1-year storm, so these are very frequent storms, then 10 years, 100 years, and then a postulated 10,000-year storm. Okay, now you pick your design basis. We pick 100 years as our storm. And then here, these are the calculated accelerations and motions of the 2 plants, the OFMP 300 and 1100, in those storms. Okay, and so the numbers that you see here for surge, eve, and pitch are in meters and degrees respectively, and so the whole thing would move up by 5 or 6 meters during one of these horrific storms, and it would pitch by about 5 degrees. By the way, are you guys familiar with this terminology, surge, eve, pitch? Is there any sailor here? So an object that floats has, a cylindrical object that floats has 3 degrees of freedom. What can it do? It can either go up and down, that's called heave. It can do this, that's called surge, or it can do pitch and roll, right? And so those are the 3 degrees of freedom, right? And so the bottom line, these numbers are actually very small. And so our folks at Savant Marine say, well, no, this is very, very stable. And for some really, really terribly bad storms, yes.
So I guess you said that the 100-year storm numbers are really stable. Are the 1,000-year numbers
10,000?
Or the
10,000. Yeah, they're pretty big. They're pretty good, excuse me, they're pretty low. Now, this is the same thing that we do also for terrestrial plants. You need to pick a design basis, and then you have a beyond design basis. You guys know what is the real difference? I mean, you have to analyze both, by the way. You can't just say, oh, it's beyond design basis, I don't care. Essentially, you design with margin, okay? So you design and you have to have a margin. If it's beyond design basis, you're still designing, but you can basically design with much lower margin, okay? So, for example, you may be familiar with the ASME vessel and, what is it called? Vessel and boiler code, right? The ASME code. So you have provisions in the ASME code for design bases, and they call it different. They have a different terminology. But basically there you have massive margins, imagine 2 or 3 to failure. That means you're really designing 3 times away from failure. Fine. But if you have a beyond design basis, so those are limiting cases, then you can basically reduce that margin down to maybe 10 or 20%. So that's a bit of a philosophical. So you're designing it, but you don't have that sort of level of comfort that you have in the other case. Okay, so the reactor, we are really reactor agnostic, as I like to say. In other words, this is a concept for an integration of a nuclear reactor in a platform. In principle, it could work with any reactor, okay? But if you think back about the design philosophy, we want to put this on a market within the next 10, 15 years. So we picked light water reactors, and we picked licensed light water reactors, in particular the AP1000 for the large one, and the 300 megawatt plant, we would take a small modular reactor that is being designed by Westinghouse. This is not certified, by the way, but it's pretty close to existing technology, okay? Think about other reactor designs, okay? What would be the advantages and disadvantages? I mean, I've sort of been beating you on the head. If you take anything other than light water reactors, you're in for 15, 20 years just for licensing. But if you think about, I don't know, safety or operations, I mean, here we are at Berkeley, and they like very much liquid salt pool reactors. You know, the work that Professor Peterson is doing in that area. So, would you, if you put a liquid salt pool reactor in this plant, would it be? What are the advantages? What are the disadvantages? What do you think?
You wouldn't have to worry about natural convection. It's already a fuel.
You wouldn't have to worry about natural convection?
Yeah, so for example, you talk about the kind of pictures like that, you wouldn't have to worry about the heat sink thing in that scenario.
Because it's...
Because that's not how it's coded. That's not your passive
yeah, it doesn't rely as
system.
much on, yeah. But, you know, more generally, why do they like that concept? Let me put it that way. Yes? Maybe you work on it. No?
No loss of coolant after.
No loss of coolant. Why? Because it's low pressure. It's a low pressure reactor, right? So you don't have to worry about that. Well, that's great for operations. I mean, imagine you don't have components, valves that can pop as easily. That's a good one. You know, that could simplify things quite a bit on a ship or on a rig like this. You know? Yes?
If you choose sodium for your salt, then you've got a massive...
Oh boy, no, yeah, sodium would be bad, because for whatever reason, if sodium comes in contact with water, right, of which there is plenty here, that would be really bad news. Yeah.
I mean, so when I think about the ship-based reactors, like the very first thing you brought up was submarines and aircraft carriers.
Yeah.
So ideally, you want the most compact design that you can have that's safe to operate in water. We already proved that that's PWRs, but we just can't enrich the fuel enough to make them more compact than an AP1000.
More than AP1000, yeah. I mean, it's a good point. For us, it was a no-brainer, right? We wanted a reactor that was established, mature relatively, so we went with a PWR. But you can think of it. So balance of plant is a steam cycle. Again, nothing new there. Interestingly, the size of the platform for the large plant, for the OFMP 1100, is actually determined by the size of the turbine. That's really what sets the radius or the diameter of the platform. This is a big. I don't know if you guys have a sense for this, but these steam turbines for large plants, they're like a football field long. This is a massive component. We talk about power transmission. So there is, first of all, a step-up transformer on board. So this is typical of terrestrial plants as well, but in our case, it's going to be on the platform. You go up to about 350 kilovolt, and that's done to reduce transmission losses. It's the same thing that is done in terrestrial plants. Yes.
Our transformer fires handle that.
Yeah, that's a good point. So there are 2 types of transformers, one with oil and one with a different material. We're thinking of the one that has lower fire possibilities, but of course,
fluid one?
Yeah, something, exactly.
That was Indian Point's one that just had a fire in 2013.
So we have both designs. To be frank with you, we haven't spent too much time into the transformer, but obviously fire mitigation on a ship or on a rig like this is a concern, but there are regulations and practices in place to handle fires. I mean, it's a big deal, but it's not it's not a showstopper.
It's usually it's the majority of deaths in the oil industry are fires.
From fires, right? Yeah. So I have a student currently that is reviewing. We have sort of. It's not a physical book these days, but there is like a huge log of accidents, and it turns out that indeed fires and also dropping loads, from cranes and so on. Those are the two largest sources of injuries and accidents. And so we're trying to learn the lessons there and see how that would apply to a nuclear plant. We talk about the cable underwater. There are many examples. There is one even in Boston, in New York Harbor, from Brooklyn to Manhattan. Over 200 megawatt for one cable only, which is incredible. 200 megawatt going for one cable for relatively short distances. Now, when you think about transmission, this is another good engineering question. You have AC or DC. You could transmit your power either with AC or DC. AC, DC, for those of you who are. So, which one do you go for?
AC.
We went for AC, but actually AC is good if you don't have to go very, very far for these underwater cables. It turns out that underwater, I'm not a EE major, so don't quote me on this, but it turns out that you induce a lot of parasitic losses with AC. So it's okay if it's a short line, say less than 30 kilometers, which applies in our case, but if you want to transmit hundreds of kilometers, then much better to go DC. But we are happy to go AC because electricity in a turbine is generated as AC, so you don't want to convert it to DC, then reconvert it, so it was a good thing. Okay, well, I'm keeping an eye on, I'm not doing well time-wise, because there are a lot of good discussions. So we now get to safety. All right, so again here, the sort of the top objectives were really inspired by Fukushima. So if you think about Fukushima, what was it? It was initiating events, it was earthquakes and tsunamis, which disabled the safety system, so they lost the ultimate heat sink, and resulted in a massive release of radioactivity, which caused people to force the government to make the decision, ill-conceived decision, to evacuate people. And so, in our case, we're really trying to address all those concerns, not because Fukushima is the only accident that can occur, but because clearly it's a very good example of what could happen in a plant and what we need to avoid. So we already talked about the elimination of earthquakes and tsunamis as accident precursors. We already sort of mentioned that in this particular case of our plant, you cannot lose the ultimate heat sink because the ocean is right there and it's connected to the heat exchanger of the reactor. And so that reduces the CDF. What is that? Core damage frequency. It's a PRA quantity, right? Pretty low. And so that deals with design bases, okay? And now beyond design bases, if you have a severe accident, you want to reduce or eliminate, if possible, any release. And should you have a release, you want to eliminate the possibility of land contamination. And I'll show you how this is done in the next few slides. Okay? So first of all, you're familiar with the concept of the fencing depth for nuclear reactors. It has many different sort of embodiments. One that is obvious is that you have multiple redundant barriers between the source of radioactivity and the environment. And so in this case, in addition to the traditional barriers, which are the cladding of the fuel, the pressure boundary, and the containment, here you also have these hulls, right? The whole thing is surrounded by, the containment itself is actually surrounded by hulls. And those are barriers, so you got two more, which is good. The same applies to the other thing. The other important thing for the fencing depth is there is an additional barrier, which is not really a barrier, is distance from population. And in a terrestrial plane, I'm just picking, I just taking this as an example. I really don't mean to pick on Turkey Point. Right? Is anyone here from Florida? Okay. Do you live next to? Do you live in the Miami area? Okay. So here's Miami. Here is Turkey Point. Beautiful plant, by the way. Works like a charm. But within the 10-mile radius of the EPZ, EPZ stands for Emergency Planning Zone, about 160,000 people. And Indian Point, which is in New York, relatively close to New York City, 270,000 people. So if you are within the EPZ, you need to be trained to respond to an emergency. So you have to be ready to evacuate if a general emergency is called upon, and so on. And so it's cost, it's anxiety, it's a lot of unpleasant things. Now with the offshore, depending on where you're siting it, your EPZ would be in the ocean. And so one very, very important benefit of this is that nobody lives in the ocean. I mean, you don't have residents, so they don't have to be trained to evacuate. That's a very big deal, actually. So what about the safety systems? Maybe more than you want to know here, but basically, as I mentioned over and over again, we connect to the seawater to the ocean through heat exchangers. And so whether you have transits or design basis accidents like a loss of coolant or even a core meltdown, essentially you're always removing your decay heat and taking out the energy using the ocean. Note the two colors that I'm using here. There is this light blue and then a little bit darker blue. Darker blue is seawater and light blue is fresh water, okay? So in no cases, even in the severe accident where you have your core that is completely melted, you have contact between, you have basically contamination of the seawater. Always stays at least 2 barriers away from your fuel. Okay, so that's an advantage. And the way these safety systems work, again, maybe too much information here, but basically they work by opening a couple of valves and then letting natural circulation to be established. And then ultimately you take the heat out, in this case, by condensation and boiling of the seawater on the outer surface of the container. So again, seawater never enters the container, so you don't contaminate. Also, in this particular case, which is of course a severe accident, the plant here is lost, right? You're never going to be able to operate a plant that has undergone an accident like this one. But what's important here is that through passive cooling on the outer surface of the containment, you're able to keep the pressure inside the containment low, which means you do not have to vent. And at Fukushima, what really released the radioactivity into the environment is that at one point, the pressure inside the containment became so high that rather than taking the risk of the containment to literally pop, they did a controlled release of radioactivity out. Okay, and in this case, you don't have to do it. So that's good news. What about security? Okay, so someone said now the threats are three-dimensional. Very true. So for a terrestrial plant, you have to worry about surface attack and air attack. Right here, you have to worry about surface attack, air attack, and underwater attack. In that sense, it's bad. Okay, so it introduces additional security concerns. But there are also some positive things about this, security-wise. What do you think? Can you think of something positive about security for this concept?
If anyone's in the area, they probably shouldn't be.
Say it again?
If anyone's in the area, they probably shouldn't be, whereas you could just walk past other plants.
Exactly. You have it's much easier to identify early, to detect threats early here than it is for a terrestrial plant, because you have unobstructed view 360 degrees around. And in fact, I'll show you on the next slide, we basically are designing it with concentric zones going out, where people or boats are not even allowed to get in, or they're monitored, or they're warned, and then ultimately, if they continue, they're going to be shot by the guards and so on. So there are some plus and minuses, but I will address subsurface, which is important in a minute here. Now, before I get to the question, one important thing is who has the authority to respond, or the authority and responsibility to respond to threats. This applies whether it's terrestrial or offshore, okay? So, naively, many in the public say, oh, can a nuclear reactor withstand, it has to be designed to withstand a nuclear explosion. Well, if there is a nuclear explosion, I think we got other problems. Okay, we don't have to worry too much about the reactor. Or do we need to design the security force at the plant to withstand the invasion of a neighboring country? Well, it doesn't apply to the US, I guess, but maybe in other countries it could. No, because those are responsibilities of the national armed forces. I mean, you can't burden a civilian facility with that kind of stuff. But smaller threats, which are not state threats, yes, that you have to deal with, at least you have to delay or slow down the attack until external intervention can be possible. And so the name of the game in security nuclear power plants and many other facilities is delay. Okay, delay until you can bring in the capital, essentially. That's it. And that's how we were designing these sort of concentric zones and so on. There was a question.
And because you talk about this, that just makes me think about fish. I guess environmentalists will argue you put a hot reactor in a very, very cold sea, and will that?
Yeah, no, that's not a good point. I should have mentioned it earlier. So this applies whether the plant is terrestrial or offshore. The water that comes out of the condenser is going to be warmer than the water that you bring in.
Mm-hmm.
So it doesn't make any difference whether it's offshore or there. There are very strict limits, which are both federal as well as state here in the US, that tell you how hot you can discharge. You cannot discharge higher because it's going to affect the marine life and so on. But interestingly, this concept has an advantage in that sense. It turns out that if you look at the temperature distribution as a function of depth within the ocean, it's warmer at the top and it becomes cooler and cooler and cooler as you go down. So what you can do here, because you're out there offshore, you can actually draw the cooler water from the bottom, allow it to rise to the same temperature of the surface, and then you're essentially going to discharge out of the condenser at the same temperature of the surface, which means you're not really doing what is called thermal pollution. That's actually a good thing. I'm not sure you can do it in every siting, but wherever you are, the water at the bottom is going to be cooler than the water on the top, and therefore you can reduce the delta T of the water that you discharge at the top.
So for fishes, it's just like another artificial monoxide on the machine.
It is. But by the way, not that we have time, but then we can start arguing: is this sort of threat to marine life real or not real? Well, if you look at the discharge of any power plant, but particularly the very famous down here, like Diablo Canyon, it has become a magnet for all sorts of marine life. They actually love it that it's a little bit warmer, right? So you got whales, you have all sorts of fish that normally would not be there, that they actually come and congregate. So, but I'm not an environmental expert, and so I can't tell, or a marine biologist, let alone, so I can't. But it seems to me that maybe some of these threats have been a little bit blown out of proportion. Let's go one there, and then yeah.
I just had a related question with regards to frequency and marine life.
Related
with regards
to?
to frequency. Did I understand correctly that
To earthquake?
when addressing frequency, you were trying to kind of fall within the middle of big waves
And tsunami waves, which are longer wavelengths. Yeah.
So does the component itself emit frequency?
Are you talking noise? Does it make noise? Is that what you're saying?
In general, frequencies that would impact marine life.
No, not really. I mean, a power plant does. It's noise. The turbine is noisy and so on. But it's an interesting question. We haven't looked into what sort of noise would propagate through the ocean. But probably you would design it such that it's soundproof in a way. It's an interesting question. Has it come up? Yeah. Good viewpoint. Let's see.
So I know you might not be done talking about this, but I'm just curious, maybe this is a silly question, but certainly it would be the host nation's military's response to all of these things, but how would you go about setting up the detection involved for delaying anything involved with subsurface threats?
Yeah, sonars. So this is all sort of existing technology which is used nowadays for ports. They have for ports of high value. They have technology that allows you to detect threats at a distance, as well as netting, by the way. So that's a barrier. It's not detection, but you have netting. So, yeah.
So the sonar is on the port, not the actual facility?
It would be. Say it again.
So the sonar is at the port or at the actual?
Well, the sonars usually are buoys, right? So it would be deployed around at a different distance. There will be a distribution of sonar buoys around the plant. So let me maybe. And by the way, this is the funny. You remember this? But so here, these are different zones, and NM is not nanometers, nautical miles. So 6 orders of magnitude, 8 orders of magnitude bigger. So the plan is here in the middle. We got these concentric zones, and so in each of these zones, there is different technology for detection and slowing down and so on. Physical barriers would be in what we call the protected area, and this could be a few hundred meters away from. So you would actually have some nettings. You would have some booms on the surface that prevents fast-moving ships from coming through. And then there are exclusion zones for larger ships. An important threat that we are considering very, very seriously is intentional collision by a large tanker. Say a group of terrorists takes control of a large tanker and intentionally crashes into it. You know, how are you going to stop it? And if it does happen, what's going to be the damage to the plane? And so we're doing finite element analysis of the crash. To see what damage you have, but also we're putting a lot of thought in how you prevent it. And an interesting idea is shown here. And so this is, like wind. Here is the wind is not there because we particularly care for the energy because it wouldn't generate much. But it's really a double. You get a little bit of energy, maybe you get also some credits and so on. But mostly this is really sort of a prevention for large ships from coming too close. So maybe an idea to look at. Yes.
Well, three things.
Yeah.
Firstly, you talked about someone else about the environment and fish and stuff. It's about the circulation of drawing water in that goes at different levels, temperature gradient. That's cool. The other thing about that is that actually, if you look at CO2 emissions on the rise, if we adopt more nuclear, we reduce CO2 emissions. Now, the carbon cycle, if there's more CO2 in the air, there's more carbonate ions in the ocean, which actually increases the acidity of the ocean, which kills more fish. So that's one sort of counter argument against that, saying, oh, it might heat it up just slightly. Well, actually, more fossil fuels are not only heating up and making the ocean more acidic.
Yeah, you're really looking now globally.
Yeah,
absolutely. So
globally.
you go nuclear versus fossil. Yeah,
yeah,
I mean,
but it's an argument that supports our cause. And the second thing is, I am struggling to see how we could disarm a torpedo that had come from, I'm not going to mention nations, subs, towards this thing. If it was, a long-range torpedo, how would you disarm that?
No, you don't disarm it, and so the torpedo has to be dealt with design of the hull.
Right, okay. So it would be like basically you brace for impact.
So we're using, this is software that is available. We're not really inventing anything. We're using software that is used by offshore again.
Okay. So they've done all the same sort of calculations on this?
These calculations are not, again, we're really not inventing anything new in terms of the security pieces.
Just slightly different risk.
It's just slightly different risk if you wish, but you can, not easily, but you can evaluate the damage done by an underwater explosion of a torpedo of some postulated magnitude and so on. So that's exactly what we do. It turns out they're not that, the double hull with all those bulkheads and so on, it's a pretty darn strong structure. Now, we did market survey, so to speak. This is maybe a little closer to what you guys are interested in. Where are you going to put it? Now, which countries, which coastlines, and so we surveyed the whole globe. And you need to have some criteria. So first of all, if you want to be within territorial waters and still have about 100 meters, because that's important for the floating and the tsunamis and all of that, well, that takes out a lot of coast, but not much. In other words, you still have a lot of coast where basically the ocean becomes deeper, close to shore, and that's where you want to put it. Okay. Other things is, well, where nuclear makes sense as an energy source, that's also where the offshore goes. Otherwise, don't put it there. There are other desirable features. Of course, while we do design for storms, the fewer the better. Away from shipping traffic and marine life. These are the big shipping lanes in the world. You see there is a lot of traffic, of course, Europe to the US, a lot of traffic, US, China to the east here, and then from the Far East into the Gulf here and then to Europe. So these are the three big regions, and maybe you don't, for sure, you don't want to put it where there is a lot of traffic, a lot of boats and ships that could go off, drift off, and countries that have earthquakes and tsunamis, I would say, are particularly suitable for this because this concept eliminates them. So if you think about the Ring of Fire, like Indonesia, Philippines, Japan, of course, China, and so on, those are wonderful candidates because we eliminate some of the threats to their nuclear plants, and so then we sort of bundle them up in different categories. You can see here. These I'll skip very happily. Public outreach, And so let's go to this one, and these are going to conclude in the next 5 minutes. So how do you commercialize this thing? Before I go to the next slide, think about whom are you going to need to go from where we are now, which is, you know, a few happy engineers and professors at MIT with a couple of consultants, to actually putting one of this unit in a, who are you going to need? What sort of companies are you going to need, right? You're going to need, you're going to need a utility because you're going to need an operator. Let me call it an operator, possibly an owner. Okay, so you're going to need a utility. What else?
Some people who said they'd be customers. Someone who's shown an interest in being.
Okay, well that's a utility, but I would say a country that wants to host it. Okay, absolutely.
A shipbuilding company?
A shipbuilding, some shipyard, right? Shipbuilding, someone that is going to do it. That's separate from, it's still a nuclear reactor. You're still going to need Westinghouse or you know, your favorite vendor to build a reactor, right? Absolutely. So that's what you need. And so, you know, think about, that's how we think about it in those terms. And so we have utility, platform designer, reactor vendor, ship construction. Someone also that finances. Okay, so some financing, Wall Street investors. And then you can slice the project according to pre-conceptual design, conceptual design, detailed design, licensing, construction and deployment of first of a kind. And these are my timelines, but you can sort of find it yourself. Is there a role for universities? You know, we'd love to think there is, but probably at one point we will be completely out of the picture. Okay, so yeah. But maybe there is a role for a company that owns the IP, and this should be, you know, sort of interesting to you, right? I mean, I think it's unlikely. I think someone mentioned Leslie Transatomic and so on. I mean, what are the chances that that company is actually going to, that the company is going to construct the plant? 10 to the minus, lower than the core damage frequency, 10 to the minus 7. But they have the IP, they're going to facilitate. In other words, they're going to be an integrator for other players, more traditional large industrial companies, to make it happen. Maybe that's the way we should think about all these, you know, startups. And you're gonna be a catalyst. You're gonna be a facilitator. So the center of a consortium. And how do you play? That's a good question for you guys. You have to have the IP, I think. Maybe there are other ideas that you thought about. So last 2 slides. What question? Say that you are the founder and owner of this small company, this small startup. Okay, and you want to develop commercially this offshore nuclear plant. What questions? All right. So first of all, what is your company going to do? I mean, of course, what's your role? How big is the market? What are the principal reasons you think we're going to call this company OFNP Coal? Okay, can achieve significant commercial success. In other words, how is the company going to make money? Where are your revenues going to come from? Do you have any ideas? You're not going to be the owner of the plant. You're not going to operate the plant. So you're not going to get directly the revenues from selling electricity. So how is your company going to make money?
Licensing new technology?
Licensing, IP, absolutely. Another idea that comes to mind is you could either sell a license, and maybe you want to do that. You could also ask for a small share of the revenues that come from electricity generation later on. And I like that because essentially it shows that you have skin in the game, right? It's almost like I'm not going to make money until this product is put online and it actually generates money for the customer, and I share, you know, the benefits with the customer. I don't want to make my money up front by just selling you a license. So these are some of the things that you may want to think about. Yeah.
I think it's a good idea to have some stake in that, because if you can move the plant, I don't know how realistic this is, but if you can move the plant, maybe the utility is regional and they're selling it to another utility.
Yeah, I agree. You could also think of utilities that operate a fleet of this, maybe worldwide. I don't know how the politics of that will work, but there are companies that now have not just national, but international fleets. I think about EDF. Duke Power, they have a lot of assets in South America, and I know you wanted to finish on all those. Duke Power, they have assets in South America. So there are companies that are starting to think more globally, and so maybe that's an approach. A lot here to read. So how can a small, thinly capitalized company expect to achieve success in an industry dominated by the government? Well, this goes back to what we just talked about. What is the role of the company? You're not going to build the plant yourself. You're probably not even going to do the detailed engineering. You need the engineer. You need the hundreds of engineers that are in Pittsburgh at Westinghouse or Arriva in Paris, and they're doing all the detailed engineering. So they're going to do it. So what's your role, right? So I guess it sort of circles around. And more here. I mean, you can read this. Will an internationally well-regarded nuclear regulatory agency take on the licensing role for the OFMP plant? So how are you going to license this? And do you want to license it differently in one country versus another? Or again, you can take advantage of the fact that this is now sort of a product for the global market and maybe have an international license if it's even possible. So a few things to think about.